Sweet. So let's move on to the final talk of this session. Niklas, what are you talking about?
Yeah. Thank you. Yes, I'm very happy to present our ideas on a new proof technique for robust property preservation. I'm looking forward to the discussion here at PriSC. Let me start with a brief motivation for secure compilation. Here we have a program in a memory-safe language like OCaml or Rust. It first allocates two local variables, x and y, and then it passes a pointer to x to an I/O library in order to read an input. Afterwards, it asserts that the other variable y did not change. If you now look at this program, you can see that the assert succeeds independently of the implementation of the I/O library. So even if the I/O library is buggy or malicious, it cannot modify y in a memory-safe language. In order to guarantee this after compilation, a secure compiler could, for example, compile to assembly with capabilities. Then if compiled correctly, a malicious target library should not have a capability for y. And then it's guaranteed by the hardware that the adversary, the malicious target library, also cannot modify y. So the goal of this line of research is to verify that such a compiler is indeed secure. That means that a target attacker cannot violate any asserts that hold in the source. In this talk, I want to focus on robust safety preservation as a criteria. We start with a secure program and link it together with arbitrary unknown code. We now call a safety property pi a robust safety property if it holds, again, when linked together with arbitrary, my pointer's not working, when linked together with arbitrary unknown code. Robust safety preservation can, for example, be proven using program logics, as shown by multiple work in literature. A compiler is now called secure in this setting if it preserves all these safety properties. So when the compiled program is linked together with arbitrary low-level code, it needs to fulfill the same safety properties robustly. In other words, a low-level adversary has no extra power compared to the source language. So this is the existing landscape. In the next few minutes, I will tell you two problems with this existing approach and how we solve them with our semantic approach. This existing landscape really works well as long as all security properties you want your compiled program to have already hold robustly in the source. But there's a situation where this is not the case. What, for example, if the source language is not secure? It could even have undefined behavior, like, for example, C. Then this unknown code here can exploit undefined behavior so that no interesting safety property holds robustly anymore. Then robust safety preservation becomes meaningless because there's simply nothing to preserve anymore. Note that a compiler can still harden the program by, for example, compiling to assembly with capabilities. So there is something interesting to prove, that a compiler correctly hardens the program, but the existing notion of robust safety preservation cannot express this. This was the first problem with the current approach we aim to solve. Before I go into the second problem, we need to take a look on how robust safety preservation is proven. This is generally done by proving this equivalent notion. So it says if there exists some low-level code that when linked together with the compiled program emits a trace T that violates some safety property, then already there needs to exist some high-level code that when linked together with the secure source program emits the same trace T and therefore also violates the safety property. So as part of this proof, one needs to resolve this existential quantifier here by explicitly constructing some source code that does the same attack as the target one. This step is called backtranslation in literature. And well, it requires work. constructing the source program explicitly is not easy. And this is the second problem we aim to solve. Backtranslation is tedious. There are two things that make backtranslation particularly tedious. First, it becomes more and more difficult when there's a large gap between the source and the target language. For example, the source language could have structured control flow, while the target language can have arbitrary unstructured jumps. Then a target adversary can crazily jump around. While this does not give them any extra power in, for example, modifying memory locations, it makes this explicit construction of a source program that somehow simulates this behavior a real mess. To the best of our knowledge, no one ever did a backtranslation proof before, bridging the gap of unstructured control flow. Another thing that makes backtranslation more tedious is when pointers are shared with unknown code. So these are reasons why existing work only studied the problem in a restricted settings. And in fact, there's many existing work on verifying secure compilers. I want to highlight some work here that specifically targets the two problems I just mentioned. First, when good components go bad by Abate et al. Targets the problem with undefined behavior. They changed the notion of robust safety preservation such that undefined behavior may only affect single compartments, while other compartments stay uncompromised. But they require the semantics of the source and target language to have a notion of compartments built in. This line of work recently got extended to a secure version of ComCert by Deepak et al., which truly is really impressive. But again, they needed to change the semantics of the source and target languages of ComCert to have these isolated compartments built in. Another extension of this line of work is secure pointers by El-Khorashi et al., who added pointer passing with unknown code. This addition made the proof really a lot more complicated. Yeah. So next, I want to explain you how we solve the problems. Remember, this was the existing landscape, where robust safety preservation was formulated as a property on the syntax of programs. Our semantic approach now starts by defining a universal contract for the target language, which is a semantic description of all possible target programs. This idea is by far not new. Our key idea builds now on top of that. We semantically backtranslate this target level universal contract to a source level simulator. This is, we semantically backtranslate the description of possible attacks to the source language, to a simulator that describes these possible attacks at a source level. In some sense, the simulator is defined similarly to a universal contract for the source language, but it does not need to be universal for the source language. So even if the source language is not secure and could even have undefined behavior, the simulator can be more precise in describing what a target adversary can do. To make sure that the simulator and the universal contract don't appear on the end-to-end result and are not part of the trusted computing base, we build a program logic on top of that to verify programs robustly safe against the simulator. Then we use this semantic approach here as a tool to get the end-to-end result that the compiled program is robustly safe when linked together with arbitrary low-level code. So our key idea is to structure the proof differently and do the entire security reasoning in the semantic domain. Next, I want to give you a high-level proof outline. Remember that we want to build a program logic that implies the safety of the compiled program, which is down arrow P here, when linked together with arbitrary low-level code. The first proof step is to prove that a universal contract is indeed universal. and that we can over-approximate arbitrary low-level code by this semantic description here. Next, we replace the compiler by a semantic wrapper that translates between the semantic domains of the source and target languages. This is, we prove the compiler correctness theorem that the compiled program refines the source program when translated by the wrapper. The next step is to prove the key security theorem, which we call semantic backtranslation. It says that we can replace the target universal contract by the source level simulator, again translated in the semantic domain by the wrapper. Finally, we combine these two wrappers here and prove the soundness of the program logic on top of that. So what is remarkable about this proof? First, compiler correctness is the only step that needs to explicitly reason about the syntax of programs and the compiler. The key compiler security proof, on the other hand, is entirely in the semantic domain, and it does not even mention the compiler at all. We are currently formally doing this proof in the ROC theorem prover. For that, we work in DimSum, which is a mechanized multi-language semantics framework by Sammler et al. Programs are given a semantics as label transition systems with call and return events for the source language and jump events for the target language. This is best explained by an example. So consider the example from the beginning before, where we have a function f that allocates two local variables x and y, then passes a pointer to one variable to a library and asserts that the other variable was unchanged. As a label transition system, this program looks like this. In the beginning, the function f waits for an incoming call without any arguments. On this incoming event, it additionally gets a heap h, where it then starts executing on. The variable allocation becomes a silent tau step, and then this call to the I/O library becomes an external call event. On this call event, we have the new heap h extended by the newly allocated variables x and y. Note that we always have the entire global heap on the events. The semantics also does not distinguish between compartments or anything like that, and it is on us to prove that the I/O library cannot modify y. After calling the I/O library, the function waits for a return, where it gets a new heap h prime from, where it then continues executing on. This assert here becomes another silent tau step, and then the function returns with the same heap h prime it got before. So this is DimSum, and in DimSum we can now define the universal contract in the simulator as non-deterministic label transition systems, which non-deterministically apply all possible attacks. The key secret of our semantic approach lies in how we define the simulator. We observe that the program logic gives directly rise to the definition of the simulator. We want the program logic to have a rule like this. This Hor triple allows you to call arbitrary unknown code as long as you pass a low points to for all arguments. The low points to means that all locations reachable from this location L are shared with the context, and you cannot have any invariance on them anymore. This also means that you need to give up the knowledge of what value was stored at this location. Now DimSum allows us to define non-deterministic label transition systems with separation logic side conditions. This means we can take the pre and post conditions of the Hor triple and place them as a side condition on their stepping relation. The simulator then looks like this. It accepts any incoming call event as long as this separation logic side condition is satisfiable. It consists of low points to for all arguments and a state interpretation for the heap on the event, together with a separation logic frame. Then the simulator non-deterministically picks any new heap h prime, such that the state interpretation can be updated to h prime, and the separation logic frame is preserved. You can see that this way we can define the simulator to be just strong enough for the soundness of the program logic, which minimizes the back translation effort. We are currently working on demonstrating our semantic approach by verifying a compiler between two languages, rec and cap. The source language is an imperative toy language with recursive functions. It has a block-based memory model where out-of-bounds access is undefined behavior, as it is, for example, common in C. And it has stack local and static variables that can be shared at runtime. The source events are call and return events. The target language is an idealized cherry-like assembly language with capabilities. It has one flat memory and for everything and everyone, and also code is in memory. As a small simplification, we assume a built-in stack, but it has been shown to be realizable with capabilities before by George et al. The events of the target language are only jump events. Then we define a wrapper in DimSum that translates between the source and target language events, and it also translates between the different memory layouts. We are in the middle of formally doing this proof in the ROC theorem prover. We already defined the universal contract and proven that it is indeed universal. This cute little bird here is the new logo of the ROC theorem prover, in case you haven't seen that yet. We also defined the simulator and built a program logic and proven its soundness against the simulator. Using the program logic, we verified a few examples, including the very awkward example, which has been a challenging benchmark for program logic since many years. What is still work in progress and what we are currently working on is the semantic back translation and the compiler correctness proof. We basically have all the ideas on paper and are currently doing the proof formally in ROC. So let me summarize. As an end-to-end result, we build a program logic that implies the safety of the compiled code when linked together with arbitrary low-level code. For that, we propose a new semantic approach. We propose a new semantic approach and do the entire security reasoning in the semantic domain. For that, we define a universal contract for the target language that is then semantically back-translated to a simulator. This simulator does not need to be universal for the source language, which enables meaningful compiler security proofs, even if the source language is not secure and could, for example, even have undefined behavior. Finally, I have shown you how we can define the simulator such that only the minimal semantic guarantees needed for the soundness of the program logic need to be back-translated, which minimizes the back translation effort. Thank you.
Working. Let's start with questions. Thanks again for the very nice talk.
Yeah, thanks. I enjoyed the talk. So, if I already have a compiler,
Yes.
like CompCert or KCML or my own favorite verified compiler,
Yes.
how easy is it to recycle those proofs here, or do I have to start from scratch?
Yeah, it's not so easy in general, I would say. Yes, so CompCert recently got extended, as I mentioned, or adapted to a secure version. And yeah, my understanding is that the proof was not easy and required a lot of work.
If they'd started after your work, could they have used your work to do it more easily?
Yeah, like our work is still in the very, very beginning. We start with a toy compiler here, but we hope that yeah, once we have these ideas developed, they help to scale up proofs in the future.
Thanks.
Yeah, thanks for the talk. So you said that like the core security proof is this refinement from unif to the wrapped sim, right? Which, as you mentioned, doesn't contain the compiler.
Exactly.
But also clearly, like to actually get a secure compiler depends on the compiler.
True.
So if my compiler isn't secure, where does the proof fail? Because it can't be the refinement between unif and sim. There's no compiler in there.
Yes. We basically refactor the proof into 2 steps. First of all, you can think of the wrapper as a semantic version of the compiler. It reflects everything what the compiler is doing in the semantic domain. And then the compiler correctness theorem is that the compiler refines the wrapper. And then we continue in the semantic domain with that wrapper and prove that the wrapper is secure in some sense.
That makes sense. Thanks.
Any more questions?
Yeah, if there's time. So very nice work. I very much like this very modular security proof for this compiler. So at the end, I guess the comparison with these more syntactic approaches is that here require or it's a question like you require the source program to either be verified or you have to trust your source simulator, right? While in previous more syntactic proofs, you could just trust the semantics of the source language.
Yes, I agree with that. That's basically true. Yes, we kind of by moving to the semantic approach, we also changed the notion of this robust safety preservation to a more semantic version, and therefore, like it does not stand by itself anymore. But we gain here that the proof gets easier because we are in a semantic setting, and we try to build a meaningful end-to-end result on top of that again by building a program logic that lets you or that implies the soundness of the compiled program against low-level code, which here again is a syntactic property again. So you get the same behavior or the same guarantee at the target level again.
If you verify your program, right?
Exactly.
Another question?
Thank you for the talk. In the definition of simulator, you mentioned that there is the satisfiability conditions on each transitions. How do you check the satisfiability of those conditions?
Where do I have the slide?
Yeah, here.
So on this slide here,
Yeah.
and
How
you're
do
asking about the satisfiability
Yeah.
thing here. So yeah, basically, so we work with iris separation logic framework, and satisfiable here means that the iris proposition is satisfiable. So this is a meta logic statement that the separation logic proposition is satisfiable, and then like when you want to call the simulator, you need to prove this precondition that you can satisfy this separation logic proposition. So you need to basically prove that on the current state interpretation of the current heap, you pass the correct low points to for all the arguments. And then, as the caller, you can then assume the post condition of the simulator, which says that it only changed the heap h prime, well, in a frame preserving way, and you get your separation logic frame back.
Okay.
Thank
you for the answer. Yeah.
All right, any more questions?
Thanks again for the talk. Thanks for the questions.
Thank you.